All right, so we've already looked at some of the properties of definite integrals, and the ones we've looked at all came from the indefinite integral, and they all involved the function we were actually integrating. So what were some of those other, let's go back. What were some of those properties? Well, if we look at these the ones we've seen, they all involve the function we're integrating. So it was f of x plus g of x. Well, what could we do? We could split that up. Or if it was f of x minus g of x, what could we do? We could split up the function and just kind of focus in on each part. Or if we had a constant multiple, what could we do in our function? We can move that constant out in front. So all three of these properties involved the function we were integrating. Nothing really here was happening with these limits of integration. Well, the next set of properties we're going to look at involve those limits of integration. So these ones are kind of different. These ones aren't really applicable to indefinite integrals because they have to do with these limits of integration. They have to do specifically with the definite integral. So these involve, all three of these involve the limits of integration. So that's a key distinction here between the ones we've already seen, which just involve the function. All right, so what does the first property say? Well, if we're doing the definite integral of f of x from x equals a to x equals b, we can actually switch the limits of integration. So we can look at the definite integral of f of x from x equals b to x equals a. It's kind of like going backwards almost. And we can do that. We can switch the limits of integration. We just have to adjust for it by putting a negative in front. So a way to kind of think of this one is if we switch the limits of integration, we put a negative in front of the integral sign. And so that's why the order matters. When we do our evaluation, the order in which we actually plug in, top number goes in first, bottom number goes in second, that order actually does matter and kind of also reflected here with this property. So if we switch these out, you have to account for that. Put a negative in front of the integral sign. Our second property here tells us what happens if the two limits of integration are actually the same. So if we're integrating f of x from x equals a to x equals a, perfectly fine to do that. But if those limits of integration are the same, well, then you end up with 0. And that should seem reasonable because if we're going to find the antiderivative and we plug a into our antiderivative, and then we plug a into our antiderivative and then subtract, well, you get the antiderivative evaluated at a minus the antiderivative evaluated at a. It just cancels out. So you end up with 0. So this one tells us if the upper limit is equal to the lower limit of integration, well, then your integral is equal to 0. No more works required. You can just automatically say, oh yeah, that thing's equal to 0. All right, now let's look at this last property here, the integral of f of x from, there's a lot going on here, so let's look at this. I don't know why that's squiggled under there. But let's look at this property here. So this one, there's a little bit more. And we're going to investigate this one in the next example. But what this says is if we have if we integrate our function f of x from a to m, and then we integrate our function f of x from m to b, what we can do, and we're adding these together, what we can do is we can consolidate these into one definite integral where we integrate our function f of x from a to b directly. So essentially what we can do, what this property is saying, is we can consolidate integrals, definite integrals. If when we're integrating, if you kind of follow along, we're integrating from a to m, then we're integrating from m to b. If those numbers match up like this, well, we can just kind of eliminate that. We can consolidate them. We can kind of get rid of this middleman number here, this m, and just go from a directly to b. So we can just get rid of the middleman. So when we're integrating, when we're doing these definite integrals, these limits of integration, you want to think of them as just sections of the x-axis. So for instance, let's think of it as just sections of the x-axis here. So let's look at this first definite integral. Here we're starting integrating at x equals a, and we're going to x equals m. So that's what this first integral is saying. That's what this first one is saying. We're integrating our function from x equals a to x equals m. Okay. Then our second definite integral is saying, all right, let's kind of start here at x equals m, and let's go to x equals b. So maybe here's x equals b. So we're going to integrate our function. We're going to continue on. We're going to integrate from x equals m to x equals b, and that's what this second integral is doing. And so instead of integrating our function from a to m, stopping, and then going from m to b, we could just integrate all the way through, starting from a and ending at b, and we'd get the same result. So that's what this last property is saying, is that we can just integrate all the way through, starting at a, integrate all the way to b, and you get the same result instead of just using these little instead of kind of dividing it up. All right, so let's try an example with this. So let's calculate the integral of f of x from 0 to 5, where we're given some information about function f of x and some definite integrals here. So we know that the definite integral of f of x from 0 to 6 is 8. And we know the integral of f of x from 5 to 6 is 7. And what we want to do is we want to find the integral from 0 to 5. And so when we see that we're dealing with these different kind of limits of integration, we're dealing with different intervals here, it helps to kind of, again, think of this as these limits of integration. We want to think of these as intervals along the x-axis. All right, so let's try it out. Let's diagram this out. Let's draw our x-axis. And so what this first one says that we know, let's see what it says. So it says the definite integral of our function f of x from 0 to 6. So here we're looking at x equals 0 to x equal to 6. And we know the integral is equal to 8. Okay. Now the second one here is telling us the integral from 5 to 6 is 7. So it's telling us information about what this integral is from 5 to 6. So we know this chunk here, and we know kind of the entire interval here from 0 to 6. And what we're trying to do is we want to find this unknown definite integral from 0 to 5. So we have this sort of unknown piece going from 0 to 5 that's what we're trying to figure out. So if we apply this property, what it's saying is that the integral from 0 to 5 of f of x dx plus the integral from 5 to 6 of f of x dx should give us, because we're kind of going from 0 to 5 and then from 5 to 6, if we eliminate that kind of just breaking point at x equals 5, if we were to integrate from 0 to 6 directly, these two quantities should be equal. So if we take this integral plus this integral, it should be equal to just going from 0 to 6 directly. All right, so now let's plug in what we actually know. We know the integral from 0 to 6 is 8. So we know that entire thing is equal to 8. We know this entire thing is equal to 7, so fill that in. And then the only one we don't know is what we're trying to find, is this integral from 0 to 5. So by filling in what we know, we have this equation now that says the integral from 0 to 5 of f of x dx, whatever that is, plus 7 should be equal to 8. And so we want to figure out what this unknown value is, so you solve for the unknown. So we're solving for this entire definite integral. We don't know what it is. So you just solve for the unknown. So how would you do this? If this was x plus 7 is equal to 8, what would you do? You would subtract 7 from both sides. That's what we're going to do here. So you solve for the unknown quantity. And when we do that, we get the integral of f of x from 0 to 5 is equal to 1. And that's because we're just subtracting 7 from both sides to get that unknown quantity all by itself on the left side of our equation. All right, so some fun games there with some of these properties. So these properties that we're looking at are gonna, we'll come back to them, because there's some more interpretations of these in sort of a geometric sense. But for right now, we'll just keep these in mind. That we have, if we switch the limits of integration, that's something we can do. We just have to put a negative in front. If our limits of integration are the same, we get 0. And if we have this number m, if we're adding two integrals of the same function, and we have this sort of matching that occurs, well, we can just get rid of that and consolidate these into one single integral. All right, so that's going to do it for our lesson for definite integrals for now. We're just seeing how to calculate them and some basic properties. We're going to kind of keep practicing these, and then we're going to come back to what this definite integral, what it's actually calculating. So we'll see some interpretations of it in a few lessons. All right. We'll see you later. Bye-bye.